Hi everyone, how you doing? Welcome back to AI Coding channel. Today I'm finally launching the second part of this series of tutorials on machine learning with C++. And as promised, it's about logistic regression. Don't forget to subscribe if you like this video, and you can support my channel through Patreon by clicking in the link down in the video description. Enjoy the tutorial. We're going to be working on top of the code from the first tutorial on ETL and linear regression. So we're going to make some changes to this code already made. We don't want to lose our previous main script, so all the main scripts are just going to be located into a new folder called main. We're also going to be using a new dataset called census income dataset, which you can find in the GitHub repository as adult data. All links are specified down in the video description section. Now, the first thing that we're going to do is to create a logistic regression folder for the logistic regression class. And we are going to be using our existing function from the ETL to read our dataset. So I'm just quickly going to show you how to do that. I clearly forgot that I no longer have a main script, but I have a main folder, and inside the main folder I have a logistic regression main script. So I just generated a linker error. So with this, we've verified that we have successfully imported our dataset and that our data contains 30,162 rows and 15 columns. As previously mentioned in the first part of this series of tutorials on machine learning with C++, we're going to be mainly using this eigen library, which is a high-level C++ library, and it's like NumPy for Python, but for C++. So our next task is to convert our vectors of strings into an eigen matrix. Now let's quickly code that. Now we can see that we have our data frame with our all our features and the last column, which correspond to the target vector. This is a binary classification problem that we have right now with this logistic regression model. And the idea behind is to classify whether someone's income is above or below a certain threshold. And we already have our target variable in the format of true or false, either 0 or 1. So we really don't want to transform that target variable. But what we do want to is to transform the features. So the next thing that we're going to do is to slightly change our normalize function in the ETL to accept whether we want to normalize the target variable or not. Let's just quickly code this by adding an extra flag to our normalize function in the ETL. Now, after normalizing our data, you can see that we have successfully normalized our features, but we haven't touched the target variable. We are soon going to get into building the coolest part, and that's building the logistic regression model. But first, let's just quickly split our dataset into train and test sets using our train test split function from the first tutorial. And you can see the result here and how we successfully divided our dataset into train and test sets. Now we're going to start building our logistic regression model. And I will follow the same approach as in the first tutorial where I was coding the math behind the algorithms. So we're basically going to code everything from scratch. We're going to implement 4 different functions: a sigmoid function, a function that we're going to call propagate, an optimization function, and a prediction function. The sigmoid function will compute the sigmoid of an input. You can follow the function down at the bottom left corner. The z corresponds to our linear function or hyperplane. Of course, the w corresponds to our weights, the x to a set of inputs or features, and b to the bias. The propagate function is a function that computes the cost and the gradient of the propagation. This function will take 5 arguments: an array of weights, the bias, the set of inputs, the target, and a lambda. We will follow the equations for forward and backward propagation that you're going to see soon again at the bottom left corner. And our aim is to return the gradient of weight vectors and biases, which are going to be denoted by dw and db respectively, and the computed cost over all examples. In an attempt to avoid overfitting, we're also going to include a regularization term. And now we're going to get into the code and just watch carefully how I map the equations to the code itself. Let's go. After the forward and backward propagation, we're going to compute a function that will update the parameters. This function will basically optimize W and B by running a gradient descent algorithm. Following the equation, in this function we will include the arguments of number of iterations for the number of iterations of the optimization loop, the learning rate, which is the alpha in the equation, and an optional flag to print the loss every 100 steps. We will return the weights, the biases, the gradients of the weights and biases with respect to the cost function, and a list of all the costs computed during optimization, which we will use to plot the learning curve. Now let's get into the code. Again, watch carefully how I map the code to the equations. Great, we finally made it to the last stage, making the prediction function. This function will predict whether the label is 0 or 1. For that, we will calculate y hat, the sigmoid of our linear input using the learned logistic regression parameters. We are going to convert the entries to 0 if the activation is below or equal to 0.5, or 1 if the activation is above 0.5. Now let's finish our prediction function and let's just put all our model together. Now we're going to put all our model together. So after splitting our data, first thing we are going to do is to initialize our parameters, the weight and the biases, and we're going to define the number of iterations, the lambda, the learning rate, and whether we want to print the cost or not, which we definitely want to. We're going to call our optimize function, and we're going to use our retrieve parameters of weights and biases to make the predictions with our predict function. we will print the accuracy of our model over the train and test sets. We have set iterations to 10,000, so now we're going to run our program and you're going to see how it trains and logs the costs after each iteration. And that's about it. You can see that we have achieved a train accuracy of 81%, more or less, and test of 82%. The same as in the previous tutorial, I didn't do anything regarding feature engineering, and the only thing that I'm going to do is now compare this result with the same setup as with the scikit-learn. Thank you very much for watching the video. Don't forget to subscribe to the channel, and I hope to see you in the next video.